Welcome to the Chemistry, Biology and Math Revision Hub. Today we are doing the Pearson Edexcel International A-Level, Chemistry Unit 6 for October 2022. Let's begin with the first question. Compound X is a solid that contains a cobalt cation and one type of anion. A small amount of X is added to the ionized water and the mixture stirred until the solid dissolves. Tests are carried out on separate samples of the solution of X. So they say complete the table. The test is, number 1, note the appearance, a pink solution. Remember this is cobalt. The pink solution is of course hexaaqua cobalt 2 plus, as you can see here. That is going to be the complex. They say add acidified barium chloride solution. This is testing for sulfate. And because we see a white precipitate, the anion present is going to be sulfate anion. The next part says add concentrated hydrochloric acid. When we add concentrated hydrochloric acid, a blue solution is going to be formed. The formula for the complex is that it is because a blue solution is going to form. The next part, add a small amount of dilute aqueous ammonia, and then a blue precipitate forms. This is addition of a few drops of ammonia, and therefore the type of reaction that takes place is a deprotonation reaction. The next part, add excess dilute aqueous ammonia to the precipitate formed in 4 until no further changes is seen. Now here we're going to have a ligand substitution reaction. So the precipitate will dissolve to form a brown solution, and this is going to be the complex formed is that due to ligand substitution reaction occurring. Moving on. In part B, another cobalt salt, which is that decomposes when heated. So the thermal decomposition produces cobalt chloride, as well as water, which is, we do not know the number of moles. They say devise an outline procedure to determine the mass of water produced from a sample of the hydrated salt in this reaction. They say you do not need to show how X can be calculated from the mass of the water. So in this experiment, we have to measure the mass. So measure the mass of the hydrated salt before decomposition, and then place it in an evaporating basin so that you can heat it strongly in order to remove all the water. In this case, to ensure that all the water is removed, you have to heat to constant mass. This will guarantee complete decomposition. And then measure the final mass of the anhydrous sample. So it means the mass of the water is going to be the difference between the mass of the hydrated sample minus the mass of the anhydrous sample. So this brings us to the end of question 1. Let us continue to question 2. In question 2, a plant fertilizer contains a mixture of sand and ammonium sulfate. We can see here. They say the percentage by mass of ammonium sulfate in the fertilizer is determined by the procedure shown. So the procedure is, step 1, 5.75 grams of plant fertilizer is added to a conical flask containing 20 centimeters cubed of sodium hydroxide solution with a concentration of 1 mole per decimeter cubed. And then ammonia is formed in the reaction. So here we have the reaction occurring. So they say in step 2, the flask is heated for several minutes to ensure that all the ammonia formed is boiled off. And then the solution containing excess sodium hydroxide is separated from the sand. The aqueous solution containing excess sodium hydroxide is then made up using the ionized water. So the excess and then 25 centimeters cubed of solution containing sodium hydroxide from step 4 is titrated with hydrochloric acid of concentration that. So here they say describe how all the solution containing excess sodium hydroxide is separated from the sand in step 3. This process is going to be filtration because sand is insoluble and the rest are soluble. As you can see, this is liquid water, aqueous, and this is going to be aqueous if it's in excess. The sand is going to be a solid. So you filter and retain the sand on the filter paper and then get the filtrate that goes through. So also you wash the sand with the ionized water to ensure that all sodium hydroxide is obtained. In the next part, describe how to make sodium hydroxide solution in step 4. Imagine if we have our sodium hydroxide in a beaker. We will use a 250 centimeters cube volumetric flask and transfer the sodium hydroxide into the 250 volumetric flask as well as the washings. And then we will top up with the ionized water to the 250 centimeter mark. And then we will mix thoroughly to obtain a solution of uniform concentration. Moving on. Here they say the mean titer was 12.75 centimeters cubed. They want you to calculate the percentage by mass of ammonium sulfate in the sample of plant fertilizer, and they've given you the relative formula mass is that which is 132.1. Here I began by rewriting the equation for the reaction that we initially had. Remember, the volume and concentration of sodium hydroxide was given, so I'm going to use this to calculate the number of moles that were initially used. So moles of added sodium hydroxide should be concentration times volume, and again initially the volume and concentration were this, so the number of moles should be 1, which is concentration, times 20 divided by 1000, and it gives us 0.02 mole. These are the initial moles, or I'll say total moles of sodium hydroxide, including those that reacted in this reaction, plus the excess that remained in order to react with HCl in the steps after this reaction. Now we need to know that the fertilizer reacted completely with sodium hydroxide because they told us sodium hydroxide was in excess. If this is in excess, it means this completely got finished. So the moles of these that were left are those that reacted with HCl. And we know in the titration, sodium hydroxide reacted with HCl to form sodium chloride and water, and this is the equation for that reaction. We also know that here the volume of sodium hydroxide pipetted was 25 centimeters cubed, yet for HCl the concentration was 0.05, and the titer volume, which we saw here, was 12.75 centimeters cubed. So I'm going to use the number of moles of this to calculate the moles of that, and the moles of these I calculate are going to be the excess moles. So to find the moles that reacted should be the total moles that were there initially minus the excess moles. So anyway, moles of HCl from this reaction are concentration times volume, which is that times that. I divide by 1000, and that was the number of moles I had. Now, based on mole ratio, which is 1:1, it means the moles of sodium hydroxide are also that. But these moles are in 25 centimeters cubed. Multiply the moles of sodium hydroxide in 25 by 10 to get the moles of sodium hydroxide in 250, and this times 10 gave me that. So the moles in 250 are the excess moles of sodium hydroxide that did not react with the fertilizer. So the number of moles of sodium hydroxide that reacted should be the total moles of sodium hydroxide that were put initially minus the moles that were left, or the excess moles, and I got this as the number of moles. The moles of the ammonium sulfate in the sample should be, of course, half of the number of moles of sodium hydroxide that reacted. So it should be 1/2 times that, which gave me this. And the mass is going to be number of moles times formula mass, which is going to be 6.8125 times 10 power negative 3 times the formula mass that was given. I got that in grams. So the percentage is going to be percentage by mass is equal to that, divide by the original mass times 100, and it gave me 15.7%. So that should be your answer. Moving on. In part D, a student carrying out the experiment did not heat the sample for long enough in step 2 to boil off all the ammonia. Explain the effect, if any, on the titer value and hence on the calculated percentage of ammonium sulfate in the fertilizer. If all the ammonia is not completely removed, it means because ammonia is a base, it's going to react with some of the HCl, and in the titration question, the volume of HCl used is going to be larger. So that is going to affect the moles in the end. So I said ammonia will be left behind and it will react with HCl. So the titer value would be larger, or more HCl will be used. Of course, some is going to react with sodium hydroxide and the other will react with ammonia that has been left. And that means we're going to use more moles. Basically, the person who is carrying out the experiment is going to think that even the moles of ammonia that reacted were actually moles of sodium hydroxide. So you will assume that more moles of sodium hydroxide were unreacted with the fertilizer in the first reaction, and we will then assume that the fertilizer had fewer moles of this, so there would appear to be a lower percentage of ammonium sulfate in the fertilizer. So lastly here they say, state how the student could have confirmed that all ammonia was boiled off in this experiment. Use damp red litmus paper. If it remains red, then you know all the ammonia has gone off. So I said by placing damp red litmus paper in the vapors coming off during boiling, if the litmus paper remains red, then all the ammonia is off. So this brings us to the end of question 2. Let's continue to question 3. Question 3. The ester ethyl butanoate is found in mangoes, so this is the ester we're talking about. They say ethyl butanoate can be synthesized from butanoic acid. The procedure is as below. In step 1, add 5 centimeters cubed of ethanol and 10 centimeters cubed of butanoic acid to a round bottom flask containing anti-bumping granules, and then add 1 centimeters cubed of concentrated sulfuric acid drop by drop to the flask. The anti-bumping granules are there to provide or promote smooth boiling. Then in step 2, heat the mixture under reflux for 60 minutes, then allow the reaction mixture to cool before transferring into a separating funnel. In step 3, add 15 centimeters cubed of cold water to the separating funnel and shake the mixture to wash the product. Remove the lower aqueous layer from the funnel. And in step 4, wash the organic layer that remains in the separating funnel with 10 centimeters cubed of aqueous sodium hydrogen carbonate solution. This is there to neutralize the excess acid. In step 5, remove the aqueous layer from the funnel and then transfer the organic layer to a dry conical flask, adding a drying agent and leave for 10 minutes, and then add more drying agent if required. Then remove the drying agent. In step 6, purify the dry organic liquid. So the first question says, calculate which reactant is in excess in this synthesis. So this is an esterification reaction in which we have ethanol as well as butanoic acid. For ethanol, the mass is going to be volume times density, and from the question we see the volume was 5 centimeters cubed, so 5 times 0.79, which is the density, gives us the mass as 3.95 grams. Now the moles of ethanol are going to be that mass divided by the molar mass, which is going to be 3.95 divided by 46, and these are the moles we get. Now that we know the moles of ethanol, we can find the moles of butanoic acid. So mass is density times volume, which is 10 times the density, which is 0.96. We get 9.6 grams. The moles are going to be 9.6 divided by 88, which is the molar mass, and we get 0.109091 moles. These react in a mole ratio of 1:1. We can see the ratio is going to be that to that, and these moles are way higher than those moles, so we can say butanoic acid is going to be in excess in comparison to ethanol. Moving on. In part B, explain why it is important from time to time, in step 4, either to invert the separating funnel and open the tap or remove the stopper. They say include an equation to justify your answer. State symbols are not required. Remember, sodium hydrogen carbonate is added to neutralize the excess acid, and in this reaction, when this sodium hydrogen carbonate reacts with sulfuric acid, we get sodium sulfate, which is a salt, and this is soluble, and then we get carbon dioxide as well as water. I could also write state symbols. This is going to be aqueous, this is aqueous, this is aqueous, and this is gas. That is going to be a liquid. So we can see this neutralization reaction is going to produce this, which is soluble. However, this gas is going to be produced, and this is going to build up. So either inverting the funnel and opening the tap or removing the stopper allows for the removal of CO2 so that you prevent the buildup of gas or pressure. So I say this reaction produces carbon dioxide gas, and this gas increases the pressure. Inverting the funnel and opening the tap is done to remove carbon dioxide to prevent pressure buildup. In part C, a student set up a separating funnel in step 5 as shown and open the tap to remove the lower layer. They want you to explain what happens and assume that the funnel is supported by suitable clamps. So here we can see there is a stopper, and then we see there is a top down here, there is an aqueous layer and an organic layer. If you do not open the tap, it's going to create some suction in there or a vacuum. So the aqueous layer will not flow out of the funnel because the stopper will prevent entrance of air into the separating funnel. So inner pressure will not be kept constant because the inside will be like a vacuum. Moving on. In part D, drying agents are used to remove traces of water from an organic liquid. They want you to identify by name or formula a suitable drying agent for use in step 5. Suitable drying agents could be anhydrous sodium sulfate, anhydrous magnesium sulfate, anhydrous calcium sulfate, or anhydrous calcium chloride, so any of these will be able to work. Then next they say, state how a student will decide whether or not more drying agent was needed in step 5. If the organic layer is still cloudy, then there is more needed. Or when you add the drying agent, if it still crystallizes or becomes crystalline, that means there is more drying agent required. So I said the liquid will be clear if there is no need for drying agent, and the drying agent will remain powdery if the liquid is dry. So this is okay to earn you 1 mark. Next, name the technique used to obtain a pure sample of dry organic liquid in step 6. This should be distillation. Moving on. In part E, the high-resolution proton NMR spectrum of ethyl butanoate is shown, as you can see here. So we can see peaks are 1, 2, 3, 4, 5. So that means there are 5 different proton environments. We can see this is split into a quartet. We have here a triplet. We have a sextet. We have a triplet and another triplet. So here they say hydrogen 1 nuclear magnetic resonance chemical shift relative to tetramethylsilane is given here. So we're going to refer to this later. Here they say explain the peaks in the NMR spectrum between 2.2 to 2.4. Now 2.2 to 2.4, let's go back here. I drew 2 lines between 2.2 to 2.4, which is going to be around this region. Because this is not an alcohol, it's not that. So it's only going to be maybe due to HCC double bond O for the ester, because of course it's not that and it's not that. So it's going to correspond to this. So I said the peak between 2.2 to 2.4 is due to a hydrogen in the HCC double bond O. We can see this is standing for only the hydrogens attached to this carbon because they're going to be HCC double bond O. So these are going to be in that region, and we can see these hydrogens or that environment is surrounded by 2 hydrogens on this side. So this is going to be the triplet. So I say the peak is a triplet, and using the n+1 rule, there are 2 hydrogens on the adjacent carbon atoms. So that could be a suitable answer. Then next they say, predict how the high-resolution proton NMR spectrum of ethyl propanoate will differ from that of ethyl butanoate in terms of the number of peaks and their splitting patterns. Now this is for ethyl propanoate. In ethyl propanoate, if I displayed it out like this, we can see there are going to be 4 peaks. I named them A, B, C, D. And then we can see this one here is going to be a triplet. We can see region A is a triplet. This is going to be a quartet. That is going to be a quartet. And this is going to be a triplet. I'm calling this a triplet because these protons are surrounded by an adjacent carbon that has 2 hydrogens. So using the n+1 rule, these are going to be triplets, while these are surrounded with a carbon having 3 hydrogens. So 3 plus 1 is 4. So we say these are going to be quartet. So the differences are here. So I say it would have 4 peaks instead of 5 because ethyl propanoate has 4 proton environments. There will be 2 quartets and 2 triplets. 1 quartet will be at 2.2 to 2.4 due to the HCCO. You can see, and again, this is a quartet and that. If this is a quartet and that is a quartet, this is the only quartet that is HCCO. The next quartet is going to be HCO. So here I said there will be 2 quartets and 2 triplets. 1 quartet will be at 2.2 to 2.4 due to the HCC double bond O. But in ethyl butanoate, the peak at 2.2 to 2.4 is a triplet. I also said there will be no sextet at 1.7. And again, here there is no sextet, yet we saw in this proton NMR they gave us here, there is a sextet we can see here. But in ethyl propanoate, there will be no sextet at 1.7 ppm. Moving on. Question 4. Ethyl butanoate reacts with water. So they gave us the equation for that reaction. And they said a student investigated the kinetics of this reaction. The procedure is as below. In step 1, 50 centimeters cubed of ethyl butanoate was heated under reflux with a large excess of water. And then after 30 minutes, a known volume was removed from the reaction mixture and placed in a conical flask. In step 3, this sample was titrated using aqueous sodium hydroxide solution. And again, this is reacting with the acid. And then in step 4, further samples were removed from the refluxing mixture at 30-minute intervals, and each sample was titrated until the titers of 3 consecutive samples were the same. So the first question says, name the apparatus which is most suitable to remove samples from the reaction mixture. This should be a pipette with a pipette filler because it's going to remove more exact values or with minor errors in comparison to using other apparatus. Moving on. So here they say the graph of the results obtained by the student is shown. So the student plotted the V final minus VT on the y-axis against time on the x-axis. This is going to be a change in volume. And then the V final is the volume of the titer at 4.5 hours. The VT is the volume of the titer at time is equal to T. So they say give a reason why V final minus VT is plotted on the y-axis of the graph rather than the concentration of sodium hydroxide solution for each titer. This is quite easy. It's because V final minus VT is proportional to the concentration of the ester, so we can use that in the place of the concentration. Moving on. Explain how the data collected indicates first-order kinetics and show your working on the graph. Here I said, based on the graph, if you go back here, you can see based on the graph, half-life is constant because from 50 to 25, the time it took was 0.725. Yet from 25 to half of that, the time it took was that. So we have constant half-life of about 0.725. So we can say based on the graph, half-life is 0.725 hours. And this half-life is constant. So it is first order with respect to the reactant. Then the next part, the student concluded that the reaction is first order overall. They want you to explain whether or not this statement is valid. Here we could say no, it's not valid because we only determined the order with respect to ethyl butanoate, yet water was also a reactant. Or we could say yes because a very large excess of water was used. And again, if you go back at the beginning, they used 50 centimeters cubed of water. That could be a large excess, leading to not considering water in the rate equation. So here they say, calculate the rate of the reaction at a time of 2 hours. Include units with your answer. And then they want you to show working on the graph. So all you need to do is draw a tangent at t is equal to 2 like I did here and find the gradient of that tangent. Then that will correspond to the rate at that specific time. So my rate was, which is the gradient, 9 minus 3, using the points I indicated on my graph, divide by, so this is changing the vertical axis, divide by changing the horizontal. It gave me this, which is equivalent to negative 8.57 centimeters cubed per hour. So an allowed answer should be between these. Moving on. And lastly, the student suggested placing ice in the conical flask before carrying out each titration. Explain whether or not this suggestion would improve the validity of the data collected. Addition of ice causes the reaction to be quenched, and that means there will be a difference in the validity because if ice is not added, then the reaction will not be quenched and the butanoic acid or the reaction would continue and more butanoic acid will be produced. Down here I said you can also say that there will be no effect on validity since the reaction takes long, which is 4 hours, because no catalyst was used. So both answers are acceptable. So this brings us to the end of question 4 as well as to the end of this paper. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.